All right, this is the third and final part for this lesson 5, looking at the particles in a matrix. And again, we're looking at this problem where we've got two different types of particles in the matrix. And we have already thresholded our images, and we've already segmented them so that we could get out the different types of particles, the black regions and the gray regions. And so we already have all the markers for those, and that's what we're going to go ahead and analyze. So one of the things we're going to need to actually do an analysis for the particle sizes, we're going to need to know how the pixels and the microns in real values scale. And so what I'm going to do is I'm going to use this matplotlib notebook command to replot my image. And the advantage of that now, by defining it as notebook, it's a live image where I can scroll around and you can see that I can get the X and Y values. These are pixels. So what I want to do is I want to grab the location here for the beginning of this 50 micron bar and the end of this 50 micron bar. And then that's how many pixels, this difference, equals 50 microns. So that's how we're going to do that. And then I want to make sure I put my matplotlib back to the inline, so this is no longer active. Alright, so I did that before, and this is just a little screenshot of the start of the line at 241 and the end of the line here at 274. So when I'm going to do my pixel to micron conversion, I've got 50 microns, and I'm going to divide that by the micron bar length, which is 274 minus 241.6. Okay. So that's my conversion. So now all of my data, which is in pixel values, I can convert into microns. And the next thing we're going to do is we are going to find on our marker list, using this region props table, which you used last time as well, to measure a variety of properties related to the marked particles. So in this case, I've got the label that was applied to them, the eccentricity, so how spherical or ellipsoid it is, the centroid. The only reason I'm grabbing this is because I want to label each particle by the label that the markers put on it, so I need to know where to put that text. So I'm going to put it at the center of the particles. The particle areas, their diameters, the orientation, the best fit ellipse to them. I can get the major minor axes and the perimeter if I want it. There's other values as well, but these are the ones that I'm going to pull out here. So remember, we've got the markers 2, which are the black regions, and markers 3 or the gray regions. So I'm going to go ahead and grab the properties for both of those, and I'm going to go ahead and convert those now into data frames in the pandas environment. So my black data and my gray data, here's the black data, just showing you again the table format. This is just the first 5 records. The first one, the position 0, label is 1. 1 is the background. So this first row I want to ignore in my analysis, because this is actually the background, and you can see a lot of pixels in the background. Alright, so let's go ahead and we'll scroll down, and we're going to go ahead and take a look at plotting this image again, but now applying each label to the particular particle. So this is just handy sometimes, especially if you want to know, if you're interested in this, a particular particle, say maybe particle 31, then we could pull the data out for just that one particle. So I like to be able to do that. So what we're going to do is we're going to go ahead and take our image that's colored 2. So 2, remember, is the black particles. And the data table we're going to use is the black data. So I did this so that my code now here and continuing on down uses just these 2 variable names. That way, when I want to analyze the gray data, I don't have to fix all of my code lines. All I got to do is come up here and change the image and the data set that I'm looking at. So that makes my life a lot easier. All right, so I got my plot commands, and then I've got this fun line. So the way that I've got to label these, and there may be a much easier way, but this is the way that I decided to just go ahead and do it, which is a little bit brute force. I'm using the Annotate command, and what I'm going to do is I'm going to go ahead and grab my labels. Oops, I don't want to move anything. And I want to grab the position. And this is basically where to put it. So I'm going to take my label here. That's the annotate, and then I'm going to put it at these two positions. These two are ultimately going to be the values for the centroid 1 and centroid 0 is what these are going to be. So that's the location of the center of each particular particle as I move through the different labels, which is this column here. All right, so this is that shorthand notation where I'm going to generate a whole list now, right, of these commands, which is an annotate command. And I'm going to make it white. I'm going to make the font size 18. I'm going to make the alignments center. And that's it. So this piece here is my annotate command. And so every time I run a new annotate command, it will apply another label. And so now I've got this in essentially a loop. So all of that is going to get done for those two variables, the label variable and position X and position Y, in the array from my data table of the columns label centroid 1 and centroid 0, starting at row 1, not row 0. So I'm eliminating the background. Okay. So I got 3 variables, and it will come in here and go in order for the 3 columns in my data table that I've given it here, and it will take those 3 at one row at a time and stick it back in here and run an annotate command. All right. And so when I just go ahead and run that, black data is not defined. I didn't run this yet, I don't think. There we go. This is what I get. And so these are all the labels that correspond to the black regions. All right. So once I've got those all labeled, this is just kind of a nicety because I can see where things are and that things are working. I could do the same thing with the gray data. So here's my gray data table. I can go ahead and run that. And then again, I just went in and changed the data and the image that I'm using, and everything else is identical. And so now here are the labels applied to all of the gray regions in my image. All right, so those again are just giving you the picture view and the labels. So let's go ahead and ask some questions about the different kinds of particles, and I'm just going to look at the gray data set. So you could certainly repeat all of this with the black data set. Okay. So again, so I don't have to change the code everywhere, I'm identifying here which data set I'm going to use. So everywhere I have grain data, I'm going to write, that's going to be the gray data set, and the markers that I'm using are the markers 3, which is the gray data set marker values that we have in this image. Okay, so first thing, maybe how many particles do we have? So how many gray particles are there in this image? Well, all I got to do is I got to take my grain data, my pandas data frame, and starting at 1, so skipping the background, I'm going to take the label column, and I'm just going to find out how long it is, because that's what's labeling each grain. And so it turns out there's 89 different rows in that data, so that's the number of grains, 89. What's the average particle diameter? Okay, well, I want to again go to the grain data, again start at row 1. This time I want to look at the equivalent diameter column. So I'm going to take the the equivalent diameter column, I'm going to convert it into microns with my conversion factor, and then I'm going to take the mean of that entire column. So when you're doing this sort of thing, you've got to make sure that you've got your parentheses around this whole data set here. Otherwise, this mean thing may be trying to take the mean of a constant. It gets very confused. So make sure you have that. And now we'll take the mean, and I'm just going to print it out. So let me see if I ran that one. There we go. And particle diameter, 13 microns. What about the average area? Okay, same thing, just take the area column. Now we're going to convert it, but we got to square it because we're doing an area now, not just a length. And I'll take the mean of all those areas now in microns squared. So there's my average area for the particles. How about the fraction amount or percentage amount of particles, of gray particles in the image? All right, so what I'm going to do is I want to first find all those interface pixels and count them. And so I'm in my markers file, and I'm taking, in the markers file, I'm taking all of the pixel positions that are -1. So that's the interface. And then I'm finding out what that length is. And then I'm going to, for the background pixels, I'm going to do that for everything labeled 1. And for the particles, it'll just be everything greater than 1. And then what I'm going to do also is I'm going to assign half of the interface pixels to the background and half to the particles. And then my total pixels will just be background plus particles, so that I can finally get the percentage by taking my particle number of pixels and divide it by the total number of pixels. So it looks like my gray phase is 18% of my image. All right, what else can we do? Some histograms. All right, let's see what the histogram looks like for the orientation of the particles. Now, the orientation is relative to the vertical. So relative to the vertical, if I move clockwise, that's a negative angle. And then if I move counterclockwise, that's a positive angle. So that's how these are interpreted. And it comes back in radians, so I want to convert that into degrees. Then I'll do the histogram on it, my orientation values. And this is what I get from -90 to 90. This could be good if there's a strong orientation dependence. So if this was a rolled sheet where all the grains were elongated in the rolling direction, then you would see a definite pattern in here where you would get, in that particular case, if the rolling direction was actually also pointing in the vertical direction, then you would get a nice distribution around 0 for the orientation angle. But that's one way of looking at whether there is some texture or preferred orientation. The other thing we might want to look at is how circular are the particles. In this case, they're clearly not at all. But if they were circular type, then this would be useful information. So I'm going to just grab that from the eccentricity value and run a histogram on it. Okay. And 0 is actually circular, and then 1 is fully ellipse. Actually, I should probably check and see exactly what the ratio for the long and short axes are for the ellipse here at 1. But this is circular. So you can see that they're not circular at all, which we expect. All right, so we got the average particle diameter, but why not look at a histogram of the particle diameters as well? And here I just did a different way of doing the histogram. I could have done this one. I know it's nice and short, but if I did want to use this for maybe a publication or presentation, then I might want a little more control. So I'm using now the matplotlib version of histogram, where this version of histogram is in pandas. So on this one, I'm going to be using plot. Right? That's my matplotlib .pyplot, and I'm using histogram there. And it outputs three values. It outputs the number that's in each bin, and it outputs where the bins are. And then I don't remember what patches is, sorry. I'll have to look that up. All right, I'm going to give it the grain data, equivalent diameter, convert it to microns. I'm going to tell it the number of bins. Density, false, means that each bin is just going to tell me how many grains or particles fall in that particular bin, where true would divide by the total number so that you had a probability of the particles being in each bin. And then we've got green for the face color, and then alpha. I don't remember alpha either. I'll have to go back and check on alpha. Okay, we can do that in just a second. So let me go ahead and do that. I got to change my Y label here because that's not right. It's not probability since I made that density false. So this is actually just a number of grains. So we'll run that. And this is what we get. So this is the number of grains that are of a given size in microns. Number of the gray particles in particular. And we turn the grid on. So this just looks a lot nicer. And then we could repeat all this with the black data. All right. Let's go ahead and take a look at this plot histogram and see what the alpha factor actually does, because I do want to know that, and maybe what patches is. So what do? I'm just going to jump on the web. I'm typing in, I guess you can't see it, but I'm going to type in matplotlib .pyplot and .histogram, or hist, just H-I-S-T, because that was what we were just doing. Here's my results. You can see I've looked it up once before already. So I'm going to go ahead and open that. And let me resize here a little bit because it's off the screen. All right. Let's go ahead and take a look. So we've got my X data. We have the bins. We already knew that. You can see the density will be in here. So there's the color. We made green. And then where's the there it is. So the density, remember we said that's false. If it's true, here's the equation it's going to use to give you the probability. And the other value we said we had was alpha. Okay, I'm not seeing alpha in there right away, so let's keep going down and we'll see what we can find. All right. Returns, so this is what it returns, n. So this is the array. This is just the list of the values for each of the bins. Okay, whether that's depending on the density, that'll be a number like we did, or a probability value. So that's that. This gives you the bins one is also an array, and it gives you the edges of the bins. Okay, so the start and stop values for the bins. And patches. So this is, let's see, a list of single polygon or list of such objects. Individual artists use create histogram or list of such containers, multiple input data sets. Okay, I don't know what patches is. That didn't help me. I'll have to look that up later and tell you. All right, but I didn't use it. Okay, let's see what else. Alpha, we're looking for alpha. So hist2d. Let's see if that gives me an alpha. There it is. All right, it's a blending value. Huh. Okay, so let's go see. So let's go ahead and make the alpha equal to 1. How about if alpha is 0? Okay, 0 is not good because it gets rid of everything. How about 0.1? Oh, okay. So this is, so you've got the grid on here, and you've got your green for the bars, and this might actually be important, especially if you had two different color bars. But you can see this is like an opacity. So this really pushes it far into the background. You could start to see here. Now you could still see the gray through here, but it gets darker and darker as you move your alpha value up. And there's 1. All right, so some sort of a blending value. All right, I think I better stop because I've gone 20 minutes. This is too long. And that is it for lesson 5.